Okay, now this oscillator, this is just one of several generators that are available in this script language. And if you open up LaserBoy Liquid Math that comes in the documentation with this, there's a list of available generators. See, there's oscillators, just one of them. And all these other ones here, they use one or more LBO, the LaserBoy oscillators, or they may just use factors to generate these figures here. You just need circular radii to do these things. But anyway, so we looked at oscillator, so let's look at a different one now. Let's look at polar, which also just uses LBO1. And let's go back to here, and let's go ahead and just replace that. Okay, so now we're calling polar the animated version of it, as you can see, because it begins with the underscore character. Now, what polar does is, okay, just looking at the oscillator LBO1 as the oscillator generator, you get the XY plot of it, which is rectangular coordinates. Polar is a different coordinate system. Polar coordinates, they start in the center of space as the origin, and you have rho and theta instead of x and y. Rho is the distance away from the origin, and theta is the angle of rotation around the origin. So it's like a radar screen view of a two-dimensional plane. So you can still locate any point in space, in two-dimensional space, using rho and theta. It's just a different way to do it. And we use the sine and cosine function to convert rectangular to polar coordinate system. That's one of the reasons why these things were developed, discovered, whatever you want to call it. Okay, so we're going to plot polar this time, but we're gonna change some things. Let's see. Let's go ahead and make the frequency 10 in both of them, and right. Okay, so now the frequency is 10. No, wait, hang on. Yeah, okay. Frequency is 10. Okay. Okay, so these are all default values except for frequency, which is 10. These are all default values except for frequency, which is 10. There's no change between the two of these things, but I'm going to change something here. I'm going to start with a duration of 0, meaning we're using none of the real number line to plug into the very first frame of our polar generator, and we're using the full circle around 2 pi for the duration of the last frame, and we're going to look at an animation of 50 frames of what this looks like. Remember, I said polar, instead of being XY coordinates this way, it's rho and theta this way, like a radar screen. So let's see what this looks like. And we get 51 frames, and you see that? You can actually see it. There's the unit circle. There's nothing because our interval is nothing. And then our interval, these are 50 iterations through the whole thing leading towards 2 pi. And you'll notice that, okay, you see how this thing, going back to the first frame, okay, you see it's heading positive as we're rotating around the circle, right? You can see there's, well, okay, there. See, it's going positive, okay? And then right here, this, right there, is where it crosses 0 again, meaning, the sine wave goes above the 0 and then it goes below the 0 and back up to, right? So this is the sine wave going up above 0, and then it's going down. This is negative. So even though we're on the radar screen thing, rho, which is the distance from the origin, can be direction this way, but magnitude negative, which means it's the opposite direction. So that's why you see this weird flipping through the origin, is because that's what a sine wave does, right? So, and this is 10 cycles of it, and there's your full 10 cycles. If you counted all of these, there would be 20 of them, because with one cycle of a sine wave, you have 2 of these loopy things, right? Okay. So not only can we watch it being rendered like we just did there, but we can also make it so that we can see the actual sine wave itself if we put the offset to, let's make it 2, so that we're, okay, now remember, offset just moves the whole thing up and down. Well, in the polar coordinate sense, it's adding to rho. So it's making everything plot farther away from the origin. So, and because it's 2, we're adding to 2, so it means the entire wave is going to be above 0. All right. Save that and render it. And see, now the whole thing, now you can clearly see the sine wave being wrapped around the circle, because it doesn't loop through the origin and go negative anymore. It's all positive. Okay, so now taking this concept a little further, let's make this, let's say 3.5. Okay, so now we're looking at a half. The frequency has a fractional part to it. It's a half. Okay, so if we look at this the way it is, it goes like that. And you see how it just kind of abruptly starts here and stops there, okay? It's because we have that half of a frequency thing. We have the fractional part of frequency. So if you think about it this way, 2 halves makes a whole. So if we want to see the whole figure as a closed loop back onto itself, it requires 2 full cycles around the unit circle, because then it would make it a frequency of 3.5 laid on top of another frequency of 3.5 is like, sort of like, it goes through 7 full cycles if you do it twice. Okay? And so you end up with and see, it finishes now. So you end up with this figure right here, which is pretty neat, okay? It's a lot like spirograph, but it's not exactly. This is a polar function graph of the sine of 3.5, the frequency of 3.5. Yes, sine with a frequency of 3.5. And an offset of 2, by the way, which is why it doesn't loop through the origin. Okay, now, starting with this concept, let's look at something that's a lot more complicated. All right, this is also one of the example text files that comes in the TXT folder. All right, this one generates an animation ultimately, and I'll show you what it looks like. Alright, there it is. Okay. Okay, let's see how we make this. Okay. All right, first thing we do, first thing that loads anything into the registers at all is this. Okay, we already know what an oscillator does. It's just LBO1 on the x-axis, right? And this is not animated, by the way. This is a single frame. And we're setting the amplitude of LBO1 to 2.5, which means we're increasing its height this way, proportionate to its length. And frequency is 1, which is the default anyway. Iterations of 500. There's going to be 500 vertices in this. Duration of 1. It's 1 cycle of a sine wave. So let's rem this out. Okay. All right. So now everything from here all the way to there is ignored, okay? And the render's still in there. Let's just take this out for a second. Okay. All right, so let's save this and see what this is. And by the way, we're also showing the unit circle. All right. And you get a sine wave, just like you would expect, okay? And then, what we're doing is this next thing, this right now is in play. Parameter called factor exists, and there's actually 4 factors. There's leading underscore, and then there's the trailing underscore, and then there's the both, and then there's this one. These have to do with, this is, instead of being distributed through a frame set, which is what creates an animation of initial frame values to final frame values, this things that end with the underscore, the trailing underscore, are within the interval of the frame itself, which means from the first vertex to the last vertex in the frame, we begin with a factor of factor, and we end with a factor of factor underscore. And in this case, we have set, by the way, the default value of all the factors is 1, meaning if you use it, use it as a factor to multiply an entire frame set, 1 has no effect. It's 1 times what it already is. Okay, so we're setting this factor to 0, right? And this is the default value of factor underscore. This time we're using acceleration, and we're using negative scale acceleration, -1, which means that as the factor is being applied to all the vertices in the frame, from the first one to the last one, it is continuing to increase in factor, in size, in magnitude, but the rate of its increase is decelerating. Let's put it that way. It's decelerating. Yeah. And we do this spread scale, and as I mentioned before, anything that begins with the word spread means that it's distributed effect from the first vertex to the last vertex in a frame. So then when this thing, okay, so this loaded the sine wave into the registers at register A. Doing this took this, did this to it, and loaded it into the register in register B. So this is now what is currently in the registers. And when this because there's nothing happens below this except for this render here, then we're going to be able to see what this is on the screen, right here, at this point in the code. All right. So this store what this does is this says, okay, whatever's in the register right now, copy it over here in this imaginary list of things. It can be whatever is in the register, okay? And we're going to call it swish. So doing that, this is going to generate an error, by the way, and I'll explain why. So let's go over here. See, it says that there was an unused frame in the frame set list, and what that means is, oops, there. And it looks like this. See now, see, it has this weird shape to it because its magnitude is it's being multiplied by a number from 0 to positive 1, and it's so that's why it's both its magnitude, but the amplitude this way is affected, but also the length of the period in which it is drawn is also affected. So you get this weird thing that I call a swish, okay? And I call it swish because I put it into this list with the name swish, okay? And the reason that LaserBoy threw an error is because we got to here and we rendered, and then that was the end of the file, and LaserBoy said, well, you never used the thing you put on the list. That's why it's an error. So if you're going to put something on the list, the whole point of it is to use it in some sort of calculation. So the next thing we do in this is we're actually calling a generator. So this is going to render a new frame set in the registers. We're saying still frames is 500. Basically, this is a still frame generator because it has no underscore leading it. So we're gonna calculate this single frame thing, but I want 500 consecutive frames of them in the frame set. Okay, the duration is 300 iterations of 2 pi, and or 300 trips around the circle, and then iterations, the number of vertices in each frame, is 50,000. All right. Amplitude of LBO1 we're setting to 1 because if you see up here we actually changed it. The default value is 1, but since we set it here to 2.5, we need to reset it here back to 1. Okay. And this frequency thing, you remember we had the whole 3.5 thing before, and that's what makes that neat little, because there's our offset of 2, right? So, we already looked at this situation. So this situation here, what happens is, because we're going around the circle, all the way around the circle 300 times, this, if you drift the frequency a little bit forward, every time you go around the circle, it's off by a little bit, and it keeps layering over itself, and I'll show you what that looks like. We already looked at polar, but we looked at the animated version of it. It doesn't matter, it's the same concept. This is the polar coordinate graph of the frequency of 3.5, offset of 2, and for 300 iterations around the unit circle. Oops. Okay, we still get the same error because we haven't used swish yet. Okay, and it looks like this because, okay, we're going around 300 times, right? And we got that drift thing going on, which if you want to see what that looks like, okay, now we've got depth going, because this is purely two-dimensional. It's just, right, it's polar two-dimensional, but we just stretched it in time, and you can see it's got the twist to it. See, each one of these things is very close to being that same figure that we got with the frequency of 3.5 and offset of 2. But it's got this twist because each iteration of it is a little bit, it's just creeping forward as it goes around. Okay, so the next thing we're going to do in the code, all right, where were we? All right, we're going to do a animated rotate. What that means is, okay, we have a set of frames that is 500, yes, it's 500 copies of this still frame. So it's just sitting there. You could, I mean, back here again, as I say, you look at this, there, yeah, sure, it's an animation, but every frame is exactly identical at this point. All right. So there's no movement. So what we want to do is we want to animate this thing by applying a rotation through the whole set of frames. An animated rotation that begins with initial values of none, no rotation at all for the first frame. And for the last frame, because the leading underscore, we want one full rotation around the z-axis, and then we call this animated version of rotate. And by the way, this is just rotate, this is not spread rotate, which means rotate rotates all the vertices within a frame exactly the same way. It doesn't spread itself through the frame or through the vertices in each frame at all. It just rotates the whole frame. But it does do this animation effect through the set of frames, which is why it begins with the leading underscore. So let's see what this looks like, and we'll render it. And it, see, now it rotates, and it rotates one full time around in all 500 frames, right? Okay. It's still just this, let's see if I can show it. Yeah, it's still this thing, right? Okay. But again, like I said, this is really a two-dimensional thing, right? It just, that's what it looks like. Okay. All right, now back to the code. The next thing we do is, whoops. All right, and in this case, we're using acceleration of +1. So this, as factor is transitioning within the interval of the frame to factor underscore, at the end of the frame, it's increasing exponentially because this is a positive number, right? And then we do this spread scale thing, and the spread scale concept is, again, it is from factor to factor underscore distributed through the vertices in a frame. If this was just scale, then it would scale everything just according to factor, but it's spread scale, so it's from here to here within the interval of the frame. And then we're going to render that. Okay. And it looks like that. And I can show you, here's it. If this is, it's still two-dimensional, right? But we're gonna look at it stretched out over time, and you can see it is an exponential curve, right? And it exists in it's only two-dimensional, but that's the order in which it's plotted. And remember, we put the one full rotation thing into a set of 500 still frames, right? And so that we get the animation of one full rotation. Well, that's still there, right? That's part of it. That's all right. So now the next thing we do is let's go ahead and, well, let's just do it that way. Okay. Recall. Remember we stored up here, store, swish. This can be any name you want as long as it complies to the has to begin with a character, can't have any spaces in it, and you can use, I think, underscores and dashes or whatever. Can't begin with a number. Okay, so we are recalling swish from the magical list. We're just saying put that in the registers, and then we're saying add. And what add means is that it literally takes, this is only one frame, as you know. This does not begin with an underscore, so this just simply does the same exact effect to every frame in the frame set that's already in the registers, which happens to be this rotated, spread scaled thing that we just did, this bit, right? Where we got. So now we're recalling swish, which is that thing, and we're just adding them together point to point along each one. This frame to that frame, which there is only one frame here because swish is only one frame. So we're adding this frame to all of the frames from this thing. Okay? And it looks like this. Because we took that flower thing, right, that did one full rotation, and we just kind of went like that along that swish. And it's offset here because of this, right? So if we take that out, take this out, right? So there's no more unit reference circle. And we might as well go ahead and put the color in this thing too, right? Oops, there it is.